let us make this one as proposition 1, this one as proposition, okay, this is proposition 1, proposition 2 and proposition 3. Okay, so delta 2 graph, okay, it will be path or cycle, yeah, that's fine. So there it is easy to prove uh, the thing we want to avoid odd cycle there. So proposition 3, if G is 2 connected, okay, so it has no cut vertex, okay, so it is 2 connected and there exists basically what he says U and V such that G minus UV is disconnected. G minus U and V is disconnected, then here also we are assuming delta is greater than equal to 3. So then what can we say about chi of G? Can we say that chi of G again delta of G? Let us try to see what will happen if suppose this is our graph and we have U and V such that disconnected, right? So this is another. So U and V, if you remove them, then basically we are going to get this here G1 and here G2. Okay, so suppose U and V are adjacent, then what will happen? Let us restrict also such that non-adjacent U and V non-adjacent U and V such that G minus UV is disconnected. Then can we say that chi G is at most delta G? How to say? Same. U and V. So how to do that? So what is degree of U? U and V are not adjacent, then degree of U is less than. What is delta of U in G1? Less than equal to delta minus 1, and what is degree of any gi, basically it is basically v is also delta minus 1, right? Is it true? Right, from here can we prove? Yeah, that is not the guarantee. Yeah, good. But uh, in uh, uh, in this is the O scenario, right? This is the O scenario. This is less than equal to delta minus 1 we are taking, right? If they are not of degree delta, then also it is less than equal to delta, right? Right, both can be also degree delta. If they are not of degree delta, then immediately you can color them, right, by the property, right? So, right, you are getting a vertex of degree less than delta and immediately you can do it, right? So, suppose they are of degree delta and they are forming the two cut of the graph, then what is the problem, right? So, degree of they are basically of delta minus 1 degree may be here also, right? So, if what will happen, if anyone is, if degree of G1U, let us say without loss of generality, anywhere it is basically less than equal to delta minus 1, then what will happen, right? Here you have basically delta minus 2, right? Then you connect this edge, right? And then you color G1, right? Color G1, what will be the G1 union UV, right? Whatever degree of U over here, degree of U will be at most delta minus 1 because we have assumed this one, right? Right? Then degree of U in G1 union this UV graph is basically at most delta minus 1, right? then we can get a delta coloring of G1. Delta coloring of G1. Similarly, what about degree of U? Right, delta coloring of, okay, delta coloring of, immediately we can say that degree of, here we are going to get a delta coloring of G, right? So this vertex of this will be how much? If you connect this UV, right? Then what about degree of U? Delta minus 1 in G1, right? So we can get a coloring of G1, delta coloring of G1. Similarly, we can get a delta coloring of G2, right? And then now if needed, you try to permute the colors so that the coloring agrees on U and V, because U and V are getting different colors because we have made adjacent. So let us say 1 and 2, after deleting also, let us say this thing, if there is need, then you permute the colors of G2 to get the coloring of G, right? So therefore we can say that here chromatic number of G will be basically at most delta in this case, is right, if this thing happens, right? So now I assume that, right, right. So in one of G1 and G2, say G1, degree of G1 of U is equal to delta minus 1, and also degree of G1 of V is equal to delta minus 1, right? So in this case, what we can do? So in this case, let us try to see, this is U, this is V, then, right? So degree in this part, degree of G1 U is delta minus 1, degree of G1 V is also delta minus 1, right? Okay, then what will happen? U is going to have only one neighbor here, right? Let us say this is U dash, okay, right? What about G minus U dash and V? This is again disconnected. U dash V is also a 2 cut, because this is the neighbor, right? This is U and V. After deleting this U and V, if you delete this U and V, then what will happen? The graph was disconnected. Similarly, if you delete this thing also, U dash and V, then also the graph will be disconnected, right? So now what is the degree of U dash in G1? It will be at most delta minus 2, right? It will satisfy the property, and then treating U dash and V dash, instead of U and V, we can get a coloring of delta coloring of G, right? The question is, already we have seen that chi G is at most delta G plus 1, right? And what are the graphs having this thing? Graphs such that chi G is equal to delta G plus 1. What are the graphs? Can you give some examples where chi g is equal to delta g plus 1? Right? So if you take C2n plus 1, right, then chi of this thing is 3, that is equal to delta g plus 1. Any other example? Chi of kn is equal to n minus 1 plus 1, that is basically delta g plus 1, right? Now question is, are these two classes of graphs the only graphs satisfying this thing, right? Are C2n plus 1 and kn the only graphs satisfying chi g is equal to delta g plus 1? So we are going to answer this, right? And the answer is yes, and that is by Brooks theorem. And what Brooks theorem says? Let G be a graph which is different than a complete graph or an odd cycle. Then chi g is at most delta of g, right? So how to prove? Can we prove? Using the proved proposition, can we say that chi g is at most delta g if the graph is different than a complete graph or an odd cycle, right? How to do that? Let us try with delta equal to 1. Delta equal to 1, okay, this is k1 is the only graph, so that is a complete graph, so we do not consider this one. Delta equal to 2, right? Delta equal to 2, we are getting odd cycles, so let us not consider this, right? Or we can prove also, except odd cycle, delta equal to 2, what are the graphs? These are basically the even cycles or path, right? And chromatic number of even cycles is 2, chromatic number of a path is also 2, right? So it is bounded by 2, right? So assume that delta is greater than equal to 3, right? Then consider case 1. G has a cut vertex, right? G has a cut vertex, then what will happen? By the proposition 2, chi g is at most delta of g, right? So G has no cut vertex, G has no cut vertex. Then what can we say about this? G has no cut vertex, then we need to consider whether G is 2 connected. G is 2 connected and right. Uh, G is 2 connected and we can say that G is not 2 connected, right? So G is 2 connected, then we will say G is not 2 connected. It is not 1 connected, not 2 connected, that means we may get more number of vertices to make the graph disconnected, right? So in this case what will happen, G is 2 connected, then you have basically UV cut, right? So UV cut, then what will happen? By proposition, right? If UV are not adjacent, by proposition. If UV are adjacent, then already we are making adjacent then, right? To make them other colors, right? So what we did in the earlier proof, we have this thing U and this is V, then we are trying to make these two adjacent and proving, right? So because of here we can say that chi G is at most delta, right, by proposition, right? Okay. Then G is not 2 connected, let us say, then G is not complete, right? G is not isomorphic to Kn. Not isomorphic to Kn means what we are going to get? We are going to get a vertex V and it is going to have two neighbors X and Y, right? Graph is connect, right? This thing we are going to get, right? Then there exists this thing such that G minus xy, what can we say about G minus xy? It is still connected, right? 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 Okay. Now you take the ordering of the vertices, you take x, y, right? So G minus xy is connected, right? So now you take a spanning tree at V and you order those vertices like this and then here V, right? So this part is G minus xy, right? This part is G minus xy, clear? Okay. Okay, now apply greedy algorithm. Then what will happen? This will be color 1, this will be again color 1, and if you color this thing, what about V? How many neighbors of V will appear before V? All the neighbors, right? Delta neighbors, and it has two neighbors which are having same color, right? So which color will be given to this vertex V? The delta color can be given to vertex V, right? So applying greedy algorithm, uh, we uh, we get a delta coloring of G in which X, Y receives same color, right? So therefore here what is happening, chi of G is basically delta of G. Okay. Okay, let us come back to that bound. Chi of G is strictly omega of G, right? Right, we have examples in which chi G is more than omega G, right? So one example is the C5, right? What about other examples? Can we, how large this can be? Minus omega G, how large this can be? Can we say that it is greater than K, where K is a large number, right? Okay, the answer can be this difference can be very large. We'll see a triangle free graph. Triangle free graph means what is the uh, omega? Omega will be 2, right? And we'll see the chromatic number can be arbitrarily large. Okay, so that is a new term we want, that is Mycelinsky graph. So basically we can get from a graph G, let G be a graph where V is the vertex set, and V, let us take x1, x2, like that, n number of vertices. Okay, so now construct a graph G dash graph, let us say it is M of G, and where what is M of G? Vertex of MG is tend to be basically vertex set of G union y1, y2, yn, z, and S set of this thing is, you take S set of G union yi xj such that xi xj is an edge of the graph, right? Union z y I is 1 to n. Okay, so what is the meaning of this? The meaning of this is this is the graph. This is x1 to xn, right? Here edges are there. So you make a copy of these vertices. This is y1 to yn, okay, and you take a new vertex, that is z. Z is adjacent to every vertex of this. This is, let us say, v. Let us say this is v dash. Every vertex of v dash, and here the edges are there in this. This is with respect to G, and if these two edges are there, this is xi and this is xj, right? Then this yi is made adjacent to xj. Similarly for yj, what will happen? Yj, xj xi is also an edge of the graph, so you just make yj xi also, right? Fine, the construction is clear, right? So you take two copies of the vertices of the graph v and v dash, a new vertex z, right? You take the edges of the graph, you make z adjacent to every yi, and the edges between v and v dash will be of this form. If xi xj is an edge of the graph, then you join the edge yi xj, okay? Then we are going to get this thing. So this graph is called basically the Mycilesky graph, okay, of a graph. So given a graph, we can construct the Mycilesky graph by this construction. So let us try to draw. Let my graph be G2, K2, sorry. Let my graph be K2, then how it will look like? This will be the scene. Then we are having two new vertices corresponding to these two, right? Then a vertex Z. This is made adjacent to these two, and this will be made like this, and this will be made like this, right? So it is basically C5, right? So if G is C5, right? So can we draw, right? So we can, let us try to draw. This is let me take, this is x1, x2, x3, x4, x5. Then we are going to have 5 vertices, then 1 vertex, right? So this is made adjacent to everything, right? Then accordingly, let us say this is y1, y2, y5, y4, y3, right? y1, y2, y3, y4, y5. Then y1 x5 will be adjacent, y5 x1 will be adjacent, right? Similarly, the edges of between this and this can be drawn, right? So here, can you observe something? If G is triangle free, then what will happen? If G is triangle free, what can we say about M of G? This is M of, right? M of C5, right? This is M of. So we are going to draw this one in a nicer form later on, maybe in the tutorial class, this thing. So MG is, then MG is triangle free, right? So if you start with G1, then Mg is triangle free. So what is the relation between chromatic number of G and Mg now? Can we relate? Can we relate chromatic number of G and Mg? For every graph, G, chromatic number of Mg is equal to chromatic number of G plus 1. How? Can we prove this one? Can we say that it is, first we need to say that chi of Mg is greater than chi of G. Why? Because this graph is sitting here, right? G is a subgraph of, this is because of G is a subgraph of M of G, right? G is a subgraph of M of G, that's why we can directly say this thing. Can we say that chi of Mg is at most chi G plus 1? How to do that? Right? We can do that, right? So you take Z a new color and Y1 you assign color of Yi is to be the colors of Xi's, right? So this can be done, right? To prove this is equal to this one, what is remaining? We need to prove right? We need to prove Mg is not K colorable, right? Using K colors, we may not be able to color Mg, right? So can you use the contradiction to prove? Mg is not K colorable. This is our G. This is the copy of G. This is Z. Yeah, how to do that? If G is, if Mg is K colorable, right? So suppose Mg is K colorable, right? Without loss of generality, let us say this phi is basically a vertex set of Mg to 1, 2 like that K, right? Without loss of generality, let us take that phi of Z is basically the kth color, right? So what about the colors assigned to this? They are going to use 1 to K minus 1, right? So let me write this set to be Y, then phi of Y will be basically 1, 2 up to K minus 1, right? Right? Sorry. Yeah. Oh, this notation is not clear. We can say that phi of Y belongs to 1, 2 up to K minus 1 for each Y belongs to Y, right? So what about this? graph G. This graph G suppose uses color K, right? Suppose this vertex xi is having color K, right? So definitely this is the yi. The neighbors of xi is in G is same as neighbors of yi in G, right? So neighbor of xi is equal to neighbor of yi in G. They agree, they have the same neighbors in G, right? So we will assign the colors of y1 to yn to x1 to xn, right? Then what will happen? By assigning, since neighbor of xi intersection vertices of G is same as neighbor of yi intersection vertices of G, by assigning colors of yi to xi, we get a k minus 1 coloring of G. Okay, and what is k? K, we need to assume that k we are taking, basically k is, let us say, k colorable. This is chi G colorable, right? So if we take k is to be chi G, then what can we say? That it is a contradiction to the fact that chi G is basically k. We are able to color them using k minus 1 colors, right? Right. So what about if you take basically G1 is K1, G2 is K2, right? And G3 is M of uh, K2, right? Like this, right? And G4 is M of G3, like this. If you take, then what will happen? Here, what is chromatic number of G1 is 1, chromatic number of G2 is 2, chromatic number of G3 is 3, chromatic number of G4 is 4, right? Like that we are going to have. If we have GK, then chromatic number of G K will be basically K, right? And K can be arbitrary. So with respect to this, we can have this for every K, there exists a triangle free graph G such that chi of G is K, right? There exists a triangle free K chromatic graph. Then we'll talk about something called degenericity. Okay, So degenericity denoted by dg is defined as this, is defined as dg is maximum of delta h such that h is a subgraph of the graph G. Okay. So what is the meaning of this one? It is, that is basically the maximum of the minimum degrees of the minimum degrees of maximum of the minimum degrees of the subgraphs of G. Subgraphs of G. Okay. Right. A graph is k degenerate. A graph G is called k degenerate if this maximum of minimum is basically less than equal to k, right? So what is the meaning of this one? Every subgraph of G has a vertex of degree at most k, right? That is basically, in words we can say that every subgraph of G has a vertex of degree at most k, right? So degenerate, can we say that, have you heard of planar graphs? Planar graphs, right, are 5 right? So how to say that this one? Planar graphs are 5 degenerate. That means every subgraph of the planar graph, given planar graph G, has a vertex of degree at most 5, right? So let G be a planar graph. Let G be a planar graph. Can you say that every subgraph of planar graph is a planar graph, right? Every subgraph of G is planar, right? Right? So Euler formula is true on some embedding of the planar graph G, right? So every planar graph, if degree of V is greater than 6, then what will happen? That is basically degree of V is greater than this for every vertex of the graph. Then what will happen? Summation of this degree of V, this is 2 times number of edges, is greater than 6 times n, right? But what is the value of this one? m is at most 3n minus 6, that is basically 6n minus 12, right. So because of that 6n minus 12, it is always less than 6n, right, for n greater than equal to 3, right, fine. So when we are talking about degree of v is greater than equal to 6, what is the number of vertices in that graph? It will be definitely at least 6, right. So for this true, so here it is a contradiction, that's why we are going to get there exists a vertex of degree at most 5 in planar graph, in a planar graph, right, fine. So because of that we can say that planar graphs are degenerate, okay. So here if the graph is k degenerate, what will be the chromatic number of the graph? If the graph is k degenerate, if G is k degenerate, then the chromatic number of G will be right. If the graph is k degenerate, then the chromatic number of the graph is k plus 1 at most. Then the graph is k plus 1 colorable. So how to do that? Right. So G is k degenerate, k is k degenerate, then can we say that there exists a vertex of degree at most k in G, because G is also a subgraph of itself, right, at most k in this thing. So now vertex, let us say this vertex v, right. So what about G minus v? G minus v is a subgraph of G, right. It is going to have again a vertex of degree at most k, right. So you pick a vertex, you write it, let us say v1 we have picked, then second v2, like that we have found out all the vertices, right. And now you see this ordering vn minus 1, like this. If you take b1, right, then what can we say about any vertex vi over here? It is going to have at most k vertices in this graph, right. So it is going to have at most k vertices in this graph, k neighbors in this graph, vi to vn, right. sorry, Vn to Vi, right, induced subgraph, right. So now I apply greedy algorithm, right. So now applying greedy algorithm, what we can say that so in this ordering every vertex has at most k neighbors in okay. So by applying greedy algorithm we can say that chi g will be basically at most k plus 1, right. How? You pick any vertex, you pick a vertex which is of degree at most k. That existence is clear. So that is V1, we write that one as V1. V2 is a vertex of degree at most k in G minus V1. No, V1 is equal to V. This is okay. And V2 is basically a vertex in G minus V1 and V2. Okay. So accordingly, we can have the ordering of these vertices. And now you reverse this ordering, then what will happen? If you go from left to right, then if you have any vertex Vi, then it is going to have at most k neighbors which has appeared before this. Okay. So applying greedy algorithm, we can say that chi g is basically at most k plus